Hello everyone, this is Mani Singh here, and this is Gate Insight EDC Tutorial 1, and this is the theoretical section. So first of all, what are these video tutorials are about? These video tutorials are to cover the whole syllabus for Gate exam and for the students who are preparing for PSUs and IES. So there are two video sections in these video tutorials. The first is the theoretical section and the second is the problem section. In the theoretical section, we are going to discuss the basic idea, working principle and functionality. That is depending on the topic. And at the end of the video, we will revise all the formulas that we discussed in this video. So in the problem section, we are going to cover the previous year problems and the extra problems. So let's start with our first subject, that is electronic devices and circuits. So first we are going to study the important values, terminology and their formulas. So first we have is the charge of electron. The charge of electron is equal to 1.602 into 10 to the power of minus 19 coulomb. Next we have is the mass of electron, that is equal to 9.107 into 10 to the power of minus 31 kilogram. And the mass of proton and neutron is equal to 1800 times the mass of electron. So from this we can understand that the mass of electron is very negligible in comparison to the mass of proton and neutron. Next we have the term electron volt. What is electron volt? And electron volt is denoted by symbol E capital V. And 1 electron volt is equal to 1.602 into 10 to the power of minus 19 joule. Here joule is the unit, which means that it's a form of energy. So it is the amount of energy that is possessed by electron. And its definition is, if an electron falls through a potential of 1 volt, its kinetic energy will increase by the decrease in potential energy by 1 electron volt. So what does that mean? It means if an electron is falling through a potential of 1 volt, then its kinetic energy is increasing and the potential energy is decreasing by the amount of 1 electron volt. So we have potential V is equal to work done per unit charge. So we can find out the work or energy as W is equal to charge into potential V. So we can put this formula as we can find out 1 electron volt. So 1 electron volt, that is the work or energy, is equal to the charge Q, that is 1.602 into 10 to the power of minus 19 coulomb into 1 volt. As you can see, 1.602 into 10 to the power of minus 19 coulomb into V potential, that is 1 volt. So we get the result as 1.602 into 10 to the power of minus 19 joule. This value is important because sometimes in the examinations they are going to ask what is the value of 1 electron volt. So remember that. Next we have is the Boltzmann constant. A Boltzmann constant is denoted by symbol capital K. And there is a definition for Boltzmann constant. We have the value of Boltzmann constant K, that is equal to 1.381 into 10 to the power of minus 23 joule per degree Kelvin. So we have a definition for Boltzmann constant. The physical significance of K is that it provides a measure of the amount of energy, that is heat, corresponding to the random thermal motion of the molecules of the substance. So basically the physical significance of K is that it provides a measure of amount of energy that is corresponding to the motion of the molecules in the substance. So remember this value because this value is important when you're dealing with thermal voltage Vt. Next we study thermal voltage Vt. Thermal voltage is denoted by symbol Vt, and its definition is, in the semiconductor, the relationship between the flow of electric current and electrostatic potential across p-n junction diode depends on a characteristic voltage called the thermal voltage, which is denoted by Vt. So in semiconductors, the relationship between the flow of electric current and electrostatic potential is basically dependent on the characteristic voltage. That characteristic voltage is thermal voltage. Remember that. And there is a relation for thermal voltage, that is Vt is equal to Kt divided by Q. Now one thing you need to remember here, that K is the Boltzmann constant and Q is the charge of electron and T is the temperature. So we can rewrite the equation of Vt as Vt is equal to T divided by 11,600. Now you may be thinking how we get this 11,600 is when you divide this charge Q divided by Boltzmann constant K, you will get the value 11,600. Now at the room temperature, we know that temperature T is equal to 300 Kelvin. So you can put the value of T is equal to 300 Kelvin in any of the above equation. You will get Vt is equal to 26 millivolt. Now remember that this is the standard value, and this value you're going to use in your problems. If the value of Vt is not given, then use Vt is equal to 26 millivolt, and if the value is given, then use that value in the solution. Next we have is the current density. Current density is denoted by symbol capital J, and it is the current per unit area of the conducting medium. So it is the division of current divided by area A. So we have the relation as J is equal to I divided by A. Here I is the current and A is the area. So we get the units as current is in amperes and area is in meter square. So we get amperes per meter square. Now one thing here, that we know that current is the rate of flow of charge, so we can write as dq divided by dt. We can also write this as nq divided by t. Here n is the number of electrons and q is the charge of electrons and t is the time here. So n is the number of electrons and t is time over here. We can put this value of I, current, in the above equation J. So we get J is equal to nq divided by Ta. Here n is the number of electrons, q is the charge of electrons, t is the time and a is the area. So as we know that time is equal to distance divided by velocity. So we are denoting distance as L and velocity as V. We get J is equal to nqV divided by LA. We put this value of time T in the above equation and we get the current density J is equal to nqV divided by LA. Now one thing you need to remember here, that n is the number of electrons, Q is the charge, V is the velocity, L is the length and A is the area. L is length or distance and A is the area. Now one thing you need to remember here, that if we multiply the number of electrons into the charge of electrons, we will get the charge density. And when you are multiplying an area with a length, you will get the volume. So we read out this equation as J is equal to rho V divided by volume. Here rho is the charge density, which is number of electrons into the charge, and volume is length into area. We also have another relation for J, that is J is equal to sigma E. The sigma is the charge, is the conductivity, and E is the electric field. Remember that sigma is the conductivity and E is the electric field. Now you are going to study more about the current density J when you are going to study in electromagnetics. So one thing you need to remember here, that this derivation that we have studied about is independent of the conducting medium. So this derivation is not depending on the medium. So the medium can be a conducting wire, can be a gas discharge tube. So remember that. Now we have the force experienced on an electron placed in an electric field. So what is the force experienced on an electron that is placed in an electric field is given as F is equal to minus Q into E. Here Q is the charge and E is the electric field. Now their negative sign represents that the direction of electric field is opposite to the direction of force. So Q is the charge and E is the electric field, and the minus sign represents that the force is in the direction opposite to the electric field. Sometimes they are going to ask that what is the force that is experienced on an electron when placed in an electric field. If you know the charge, if you know the electric field, you can find out the force. Now the velocity of electron. Velocity of electron is given as small v is equal to square root of 2q capital V divided by m. Here small v is the velocity and q is the charge, capital V is the potential, and m is the mass of electron. So how you find out this velocity, the relation for velocity? First you need to know is kinetic energy. Kinetic energy of electron is equal to half mv square. M is the mass of electron and v is the velocity of electron. And the potential energy of electron is given as the charge q into potential v. If you relate both the energies, both are energy, this is kinetic energy, this is potential energy. When you equate both of the equations, you will get the velocity as is equal to square root of 2q capital V divided by m. Now the force experienced by the electron due to the magnetic field, that is given as Fm is equal to bqv. Here B is the magnetic field strength, Q is the charge of electron, and V is the velocity of electron. So sometimes they are going to ask that what is the force experienced by electron due to the magnetic field. So if you know the magnetic field strength, you know the charge, and you know the velocity, you can find out the force experienced on it. Next we have is the electric field intensity. Electric field is denoted by symbol capital E, and E is equal to minus dV by dx, which means that it is the rate of change of potential with respect to the distance. Here the minus sign represents that as the distance is increasing, the electric field decreases. So there is a unit for electric field, that is volt per meter, because this is the ratio of potential divided by distance. So the negative sign represents that the field will decrease with the distance. And the field intensity always flows from positive terminal of the battery to the negative terminal of the battery. That is important to remember. So we can see from the diagram, there is a diagram representation for that. We have a semiconductor bar here, and we have connected a cell with it. So what we can see is that the direction of electric field is from positive to negative, as we have studied, and the electron direction is opposite to the electric field, because electron is having a negative charge. So because of the negative terminal, the opposite force is going to apply on the electron. So electron is going to move in opposite direction to the field. And you can see hole is moving opposite to the electron because hole is having a positive charge on it. So we can make the conclusion from it, that is, the direction of electron is always opposite to the direction of the field, and the direction of hole will be in the direction of the electric field, and electrons and hole always move in the opposite direction. And the magnitude of electric field is given as mod of E is equal to magnitude of voltage existing divided by distance of spacing. So if you have a semiconductor and you know the magnitude of voltage existing across it and the distance of spacing, then you can find out the magnitude of electric field. Next we have is the mobility. Mobility is denoted by symbol mu. So it is defined as the steady state drift velocity per unit electric field. So it is the ratio of drift velocity divided by electric field. And the mobility indicates how fast the charge carriers will be moving from one place to another place, For high conductivity, one of the requirements is high mobility. So mobility is indicating that how far the charge carrier is moving, and if you want high conductivity, then mobility must be higher. And mu is equal to drift velocity divided by field intensity. So drift velocity is also called drift speed. There is one more term for drift velocity, that is drift speed. And mu is equal to Vd divided by E. Here Vd is the drift velocity and E is the field intensity. So the unit for mobility mu is equal to meter square per volt second or centimeter square per volt second. You can put the value of velocity as meter per second and electric field as volt per meter. So when you put that, you will get meter square per volt second. So electron and hole mobility for germanium and silicon. Now one thing you need to remember here, that the germanium and silicon are nothing but the intrinsic semiconductor. We will study more about germanium and silicon, but till now we need to know this. And we know the electron mobility, that is mu e or mu n. We represent the electron mobility as mu e or mu n. For germanium, that is 3800 centimeter square per volt second, and for silicon it is 1300 centimeter square per volt second. What does that mean, electron mobility? It means that how fast the electrons are moving, and for hole mobility is how fast the holes are moving. We will study more about what are holes, what are holes, and what is the function of them in the semiconductor. So till now we need to remember that what is hole mobility. Hole mobility is denoted by mu h or mu p, and it is 1800 centimeter square per volt second for germanium and 500 centimeter square per volt second for silicon. Now remember that these two mobilities, electron mobility and hole mobility, are very important because they are directly going to ask that what is the value for germanium and what is the value for silicon. So for germanium, if we divide the electron mobility divided by hole mobility, we get the ratio as 2.1, and you can find out by dividing 3800 divided by 1800, you will get the value as 2.1. And for silicon, if you divide the electron mobility divided by hole mobility, you will get the result as 2.6. You can divide 1300 divided by 500, you will get the result as 2.6. So this topic is important because directly they are going to ask the value in the examination. So remember these values. Now the electron mobility is large in both germanium and silicon than the hole mobility. So we can see that the electron mobility in both the cases, for germanium and silicon, the electron mobility is greater than the hole mobility. So it means that hence electron can travel faster and also can contribute more current when compared to hole. So this is we are able to understand from this is that electrons can travel more faster because they have the higher mobility. So mobility of charge carriers decreases with temperature. So as the temperature increases, the mobility of charge carrier decreases. And what is the reason behind that? We will see. As temperature increases, the atom in the material will vibrate, and due to this, the thermal vibrations, mobility of charge carriers will reduce. Basically, what happens when charge carriers are moving in a semiconductor or in a material? We take a material. What happens when the temperature is increasing? Then there is thermal vibration in the atoms. Because of that, they cause an obstacle for the movement of charge carriers. So because of that, the mobility of charge carriers reduces. So you need to remember here that mu is proportional to t to the power of minus m. We give the mobility with this relation. Mu is proportional to t to the power of minus m. Here minus m indicates that there is a decrease in the mobility. So one thing you need to remember, that this consideration that we are taking is for the temperature that is in between 100 Kelvin to 400 Kelvin, and this is without any scattering effect. Till now we are not studying that Is there any scattering effect on the mobility? We will study further. So, and mobility, this m that is in this equation, we get mu is proportional to t to the power of minus m. This m is a constant and is given by m is equal to 2.5 for electrons and is equal to 2.7 for holes, and m is equal to, that is for silicon, and m is equal to 1.66 for electrons and 2.33 for holes, that is for germanium. So remember these values because it is important. You can find out the mobility if you know the value of m and the temperature. You can find out the mobility with the help of these values. So mobility decreases with temperature as a non-linear variation. So there is no linear relationship, there is a non-linear variation. So as the temperature increases, so the mobility decreases. And this effect that we have studied of temperature effect on the mobility is without scattering. Remember that. Next we have is the mobility versus electric field. Now we are going to see that what happens if we increase the electric field, what will be the effect on mobility. First we see for the smaller electric fields, that is less than 10 to the power of 2, we have the mobility remains constant. After that there is a non-linear change that is in between 10 to the power of 2 to 10 to the power of 4, and that non-linear change is mu proportional to 1 divided by square root of electric field. After that, when larger electric field is applied, that is greater than 10 to the power of 4, the mobility starts decreasing. So there is a decrease in the mobility, and it is with the inverse relation. That is, mu is proportional to 1 divided by E. And at the very large electric field, that is at 10 to the power 7, the mobility saturates. So this is the curve you need to remember. First, the smaller electric field, the mobility is constant, and in between 10 to the power 2 to 10 to the power 4, the mobility is having a non-linear change, and after that there is an inverse relationship between mobility and electric field, and after very large electric field at the 10 to the power 7, the mobility saturates. So when smaller field intensities are applied to the semiconductor, then the mobility of charge carriers will remain constant. So we have a relation that mu was equal to Vd divided by electric field E. So we can write that drift velocity Vd is equal to mu into E. So we know that for smaller field intensities, the mu is constant. As we have seen in the graph, the mobility is constant. So if you put mobility as constant, so drift velocity linearly increases with the electric field. Remember that. If we put the value of mu as constant here, then there will be a proportional relationship between Vd and E. So the drift velocity will linearly increase with the electric field. So for electric field between 10 to the power 2 to 10 to the power 4, the mobility varies with the relation mu is proportional to 1 divided by square root of electric field, as we have seen in the graph. And for higher electric fields, the mobility of charge carriers decreases with mu is proportional to 1 divided by E. That is the inverse relationship. So here we can see that mobility is decreasing and electric field is increasing. So one value is increasing and one value is decreasing, one value is decreasing, one value is increasing. So multiplying both of them, we get a constant value. So for higher electric fields, the drift velocity remains constant. So Vd enters into saturation and hence becomes constant. So one thing you need to remember here, we can recall that for the smaller electric fields, the mobility mu is constant. So we have a linear relationship between drift velocity and electric field, and in between there is a non-linear change, so there will be a sublinear change in the Vd. And For higher electric field, there is a constant value for VD. VD enters into saturation after that. So we can see this through the graph. This is the graph, as I told you, that first there is a linear relationship between VD and electric field. This graph is between VD and E, and because mobility was constant at smaller electric fields, so there was a linear relationship between VD and E. As electric field is increasing, VD is increasing. After that, there is a sublinear change because of there was non-linear change in the mobility and electric field graph. And after that, there is VD becomes constant. As I've told you that electric field is increasing and the mobility is decreasing, so there is a constant VD. After that, VD enters into saturation. So we can see through the graph, first linear, then the sublinear, then it becomes constant and enters into saturation at very high electric fields. So in a semiconductor, as the field intensities are gradually increasing, the drift velocity first linearly increases, then sublinearly increases, and then enters into saturation with larger field applied. So the effect of doping on the mobility of charge carriers. In an intrinsic semiconductor, the atom concentration is less, but when the semiconductor is doped, the atom concentration increases, and this will reduce the mobility of the charge carriers. So in a semiconductor, the atom concentration is less, but when you're going to dope, doping is basically adding of impurity. You're adding impurity. So whenever you're adding impurity, the atom concentration increases. We will study more about doping in the further discussion. So mobility of charge carriers always decreases with doping. So the mobility of charge carriers always decreases with doping because the number of atoms is increasing. So because of that, the charge carriers are going to face obstacles. Because of that, there is reduction in the mobility. So as we can see throughout the curve, that this is mobility, this is doping concentration, and there is a downward change. One thing you need to remember here, that we never change mobility. Whenever you have a question and there is doping concentration, they're increasing the doping concentration, we never reduce mobility because we don't have any relation between the doping concentration and mobility, that how much mobility reduces with increase in the doping concentration. So use the mobility as it is given in the question. So as you can see, yes, but in the theoretical aspects we can see, yes, the doping concentration increases, the mobility is going to reduce for both hole mobility and electron mobility, both reduces. Now we are going to study the effect of scattering on mobility. So in a semiconductor, the most important scattering mechanisms are impurity scattering and the lead scattering. There is one more scattering, that is surface scattering, that is out of our syllabus. We are only going to study the impurity scattering and the lattice scattering. So now we are going to see what is the effect of mobility due to the impurity scattering. When the temperature increases, then velocity of electron increases because of the scattering of the electrons by impurity doping is less and increases with the temperature. So basically what happens when the impurity doping is less, then when the temperature increases, the velocity of electron increases due to the scattering. This scattering is the impurity scattering. This is the reason for the excess in the velocity of electrons. So because of impurity scattering, as temperature increases, the mobility also increases with the relation. There is a relation for that, that is mu is proportional to T to the power of minus of n. So recall that in the discussion when we have studied when the temperature was increases, when we are not talking about the scattering effect, at that time you can see that the mobility was proportional to T to the power of minus of n. But now we are talking about the scattering effect, and in the impurity scattering we have a proportional relation, that is T to the power of M. There is no minus M. Remember that. So in the impurity scattering, we have a relation mu is proportional to T to the power of M. So now we are going to see the effect on mobility due to the lattice scattering. So as the temperature increases, now that effect was for the lower temperatures. As you increase more temperature, then lattice scattering is going to occur. Now, as the temperature increases, oscillation frequency of the atoms at the lattice point increases, and this causes electrons experiences more collision per second, which in turn causes mobility to reduce, and due to the lattice scattering, the mobility of the charge carriers decreases with temperature with the relation that is mu is proportional to T to the power of minus M. What they are discussing here is that as the temperature increases more further, there is an oscillation in the atoms. Because of the oscillation in the atoms, what is going to cause is there is a collision of electrons. So as the collision increases, the mobility is going to reduce, and which is given with the relation mu is proportional to T to the power of minus of M. So remember that in the impurity scattering, we have the relation mu is proportional to T to the power of M. So the mobility was increasing at that time, and now due to the lattice scattering, the mobility is decreasing. So hence, because of scattering mechanism in the semiconductor, first the mobility increases because of the impurity scattering, and then decreases because of the further temperature increase and lattice scattering occurs. So we can understand from this discussion that first, due to the impurity scattering, the mobility increases. Then because of more temperature increases, there is oscillations in the atoms, and because of that there is lattice scattering, and because of that the mobility decreases. When previously in the impurity scattering, we have the relation mu is proportional to T to the power of M, and in the lattice scattering we have the relation mu is proportional to T to the power of minus M. Now the effect of scattering on mobility graph, that is given as this. We can see that as the temperature is increasing, as I told you, first because of impurity scattering, less impurity, there is a relation that is T is proportional to T to the power of M. So first the mobility increases. Then after that, as the temperature further increases, there is oscillation in the atoms, and because of that the mobility decreases. So mu is proportional to T to the power minus of M for lattice scattering. For impurity scattering, mu is proportional to T to the power of M, and for lattice scattering, mu is proportional to T to the power of minus M. The resultant mobility is due to the scattering in the semiconductor because of various scattering mechanisms like impurity scattering, lattice scattering, and surface scattering. The resultant mobility of the charge carrier is given as. Now remember, there is resultant mobility that you're going to get because of these different scattering mechanisms. There are different mobilities you're going to get. So the resultant mobility you're going to get is 1 divided by mu resultant is equal to 1 divided by mu impurity. This mobility is due to the impurity scattering, plus 1 divided by mu lattice, that is due to the lattice scattering, plus 1 divided by mu surface. If surface is given, then use that mobility, and if that is not given, then only use the impurity and lattice mobility, and you get the resultant mobility. Now, one thing you need to remember here, that the resultant mobility that you're going to get will always be less than the least value of these mobilities. Means you get any of the mobility here, means there will be lattice mobility, that will be the surface mobility, that will be the impurity mobility. So resultant mobility will always be less than the least value of these. Remember that. So next we have is the revision. Now we are going to revise, quick revision we are going to go through, and we are going to study all of the formulas that we have studied till now. First was the charge of electron, that was equal to 1.602 into 10 to the power of minus 19 coulomb. Next we have is the mass of electron, that is equal to 9.107 into 10 to the power of minus 31 kilogram. Next we have is the mass of proton and neutron, that is equal to 1800 times the mass of electron. And 1 electron volt was equal to 1.602 into 10 to the power of minus of 19 joule. K is the Boltzmann constant, that was equal to 1.381 into 10 to the power of minus of 23 joule per degree Kelvin. We have the relation of Vt. Vt is equal to Kt divided by Q. The K is the Boltzmann constant, T is the temperature, and Q is the charge. And Vt can also be written as T divided by 11,600, that we get by division of Q divided by K. And Vt is equal to 26 millivolt, that is at room temperature when we have T is equal to 300 Kelvin. And current density J is equal to I divided by A. I is the current, A is the area. And J is also equal to NQV divided by LA. N is the number of electrons, Q is the charge of electrons, V is the velocity, L is the length, and A is the area. And we get the result as rho V divided by volume. I told you length into area is volume, and number of charges into the charges charge density rho. And there was one more relation for J, that was equal to sigma into E. Sigma is the conductivity and E is the electric field. Now the force is equal to minus Q into E. That was the force when experienced by the electron when electron placed in an electric field. And the negative sign here represents that there is opposite motion of the electric field from the force. Here Q is the charge and E is the electric field. And velocity is given as velocity of electron is given as small v is equal to square root of 2q capital V divided by m. Here Q is the charge, capital V is the potential, m is the mass of electron. And the kinetic energy of electron is equal to half mv square. M is the mass and v is the velocity. Potential energy of electron is charge Q into potential V, and we get the velocity by equating both the kinetic energy and potential energy. We can find out the velocity V. Now the force that is experienced by electron when placed in the magnetic field is given as Fm is equal to BQV. B is the magnetic field strength, Q is the charge, and V is the velocity of electron. We have found out that electric field was equal to minus dV by dx. That was the rate of change of potential with respect to distance, and negative sign here represents that as the distance increases, the electric field decreases. And the magnitude of electric field is given as mod E is equal to magnitude of voltage existing divided by distance of space. Mobility mu is equal to Vd drift velocity divided by electric field. And electron mobility, that is mu E or mu N for germanium, that is 3800 centimeter square per volt second, and for silicon, that is 1300 centimeter square per volt second. And hole mobility mu H or mu P is equal to 1800 centimeter square per volt second, and for silicon, that is 500 centimeter square per volt second. And the ratio of the electron mobility to hole mobility for germanium is 2.1, and for silicon, mu N by mu P is equal to 2.6. And mobility is proportional to T to the power of minus of m. That was without scattering. When the temperature increases, there is vibration in the molecules, in the atoms. Because of that, the mobility decreases. And this relation was for the temperature between 100 Kelvin to 400 Kelvin, and that was without scattering. Now the value for m was m is equal to 2.5 for electrons, 2.7 for holes, that is for silicon, and m is equal to 1.66 for electrons and 2.33 for holes, that is for germanium. And the effect on mobility due to impurity scattering is mu is proportional to T to the power of m. As I've told you, because of the impurity added, as the temperature increases, there is impurity scattering. Because of that, the electrons speed up. So mobility increases, mu is proportional to T to the power of m. And as the temperature further increases, there is oscillation in the lattice level, there is oscillation in the atoms, and because of that, there is collision of electrons, and because of that, the mobility decreases. With the relation mu is proportional to t to the power of minus 1. That is the lattice pattern. Next we have the relation that we get the resultant mobility, that is 1 by mu resultant is equal to 1 by mu impurity plus 1 by mu lattice plus 1 by mu surface. So this, I told you that the resultant mobility must be less than the least value of these mobilities. And now we're going to revise all the graphs that we have studied. First graph that we have studied was the relation between mobility and electric field. At the smaller electric field, that is less than 10 to the power 2, the mobility remains constant. After that, there is a non-linear change in the mobility as the electric field increases in between 10 to the power 2 to 10 to the power 4. That mobility is proportional to 1 divided by square root of electric field. As there is larger electric field is applied, that is more than 10 to the power 4, the mobility decreases as the electric field increases. So there is an inverse relation between mobility and electric field, that is mu is proportional to 1 divided by E. And at very large electric field, that is 10 to the power 7, there is the mobility saturates. Next we have is the relationship between Vd and E. As I've told you that the mobility is constant for small electric fields, so because of that there is a proportional relationship between Vd and E. So there is a linear increase as the electric field increases, the Vd also increases, and then there is a sublinear change. After that, Vd becomes constant because as electric field is increasing, the mobility decreases. So one is increasing and one is decreasing. So Vd becomes constant. And after, when higher electric field is applied, then Vd enters into saturation. So there was one more relation of mobility with the doping concentration. As we were increasing the doping concentration, the mobility decreases as the number of atoms decreases. They appear as obstacle for the movement of charge carriers. So the whole mobility is going to decrease and electron mobility also decreases. And there was the relation for mobility and temperature when scattering is there. So for the impurity scattering, there is increase in the mobility, and as the temperature increases further, there is decrease in the mobility. As you can see in the graph, for impurity scattering, the relation is mu is proportional to t to the power of m, and for lattice scattering, the relation is mu is proportional to t to the power of minus 1. One thing you need to learn, that is the quote of the video. I always have a quote at the end of the video. So this is the quote of the video. This is by Albert Einstein. He was the greatest theoretical physicist. He published 4 papers. He is known mainly for the theory of relativity and E is equal to mc squared. So you can learn a lot from his life, and his quote is, try not to become a person of success, but rather try to become a man of value. I think this quote has a great deep meaning. Thank you. And if you like this video, please like and subscribe. Thank you.